So welcome to my talk on certified evaluations of Holder continuous functions at roots of polynomials. My name is Jonathan Hauenstein, and I want to thank the organizers of the Maple Conference for putting together this wonderful set of talks. So we know that the roots of the polynomials describe where interesting behavior happens. For example, suppose we want to minimize this function. Then we want to find its critical points so that f prime is equal to 0, and then evaluate the function at those critical points to find the minimum. So these roots of this derivative tell us the interesting behavior in terms of mins and maxes as well as saddle points. Not only just trying to minimize a function, but there are other applications that involve evaluating a function at a root of some other polynomial. And so the goal of this work is to develop an algorithm as well as software for certified evaluations of functions at roots of a polynomial. And this is joint work with Parker Edwards, who is a postdoc at Notre Dame, and Clifford Smyth, who is at University of North Carolina, Greensboro. So one way that we can look at evaluating g of x at a solution of p of x equal to 0 is by solving this equivalence system. So we can add a new variable y and say y minus g of x is equal to 0. So when g is an analytic function, there are many classical methods that allow us to compute bounds on the evaluation. So you can use root isolation bounds, interval arithmetic, Kantrovich theorem, Smale's alpha theory, to be able to give certified bounds on the function evaluated at those roots. However, we want to move on to a broader class of functions, more than just analytic functions. For example, if we're thinking of L1 minimization, we need to be able to evaluate absolute value function, which is not analytic at 0. We want to also be able to evaluate roots, so the nth root function, as well as functions which are continuous but nowhere differentiable, such as the Weierstrass function. So the ability to handle functions which are continuous but not analytic gives us this broader class of functions that we want to study. So the class of functions that we're going to consider are the Holder continuous functions, which is developed by Otto Holder. And so the idea is that there exists a constant c called the Holder constant and a value alpha, which is strictly positive, called the Holder exponent, such that when you evaluate your function at 2 points, that's at most c times the distance between the 2 points raised to the alpha. So this is a generalization of the Lipschitz continuous function. And in the Lipschitz, the exponent is 1, and the constant c is called the Lipschitz constant in that context. But we'll just refer to it as the Holder constant with Holder exponent equal to 1. So for example, the absolute value function is both Holder continuous and is Lipschitz continuous because the exponent is 1. It has a bounded derivative, 1 and minus 1, everywhere except at the origin where the derivative is not defined. The root function is also Holder continuous. And if n is bigger than 1, then 1 over n is strictly less than 1, so it's not Lipschitz continuous. And in particular, we can see it's not Lipschitz continuous because its derivative is unbounded because it has a vertical tangent at the origin. So this gives us a generalization of Lipschitz continuous functions to be able to consider a broader class of functions. We don't need the derivative to be defined. We just need to have a control of this exponent. And then last is this is an example of a Weierstrass function. And in this case, it's Holder continuous, shown here in the lower right, and the alpha value is given there. So it's nowhere differentiable, but it is Holder continuous. And so that means you can bound evaluations of this by just knowing the distance and this exponent. So what we want to do is we want to compute certified evaluations of this function g at roots of a polynomial p, and let's assume that the coefficients of p are rational numbers so that we have an exact equation that we're trying to solve, and then we want to take those and evaluate it at g. Of course, once p has degree 5 or higher, there's no general formula for the roots, so we're going to have to do this using approximations. So the first step is to compute some isolation bound. So we want to approximate each root. And so the first step in our procedure is to always reduce down to the simple case. So we use Maple to be able to compute a square-free factorization so that we only have simple roots to consider. And then we switch from the complex numbers to R2 and do real root isolation in R2 by taking the real and imaginary parts of P of x plus Iy and solving those two equations, those two polynomials on R2. So this gives us a real root isolation in R2, and that gives us something that we can then transform by G in order to get bounds on the evaluation. So at each of these prospective roots, we evaluate the Holder condition to give us evaluation error bounds for G. Of course, G could be a function that we can't even evaluate exactly for rational input. So if we put in a rational number, we might not be able to evaluate exactly. And so we can add in our numerical error to make this bound bigger so that we both contain the evaluation error from not being exactly at the root, as well as the numerical error from not being able to evaluate exactly. And so let's look at a very simple example, illustrative example. Suppose we want to evaluate the cube root at the solutions of x equal to 0. Of course, the exact root is x equal to 0. But let's say for sake of illustration, we compute this approximation 123 over 100,000. And we say that this has an error of plus or minus 10 to the minus 2. So then we evaluate our function at that rational value. Since we can't compute the cube root exactly, we also have an error coming from this numerical evaluation. And in this case, we can say, for example, this value listed here is correct up to 6 decimal places. Then we have a Holder bound. We know the distance from x star to x. We have this upper bound on that distance. And we know its Holder exponent is 1/3 with Holder constant 1. So we have a Holder bound of 10 to the minus 2/3. Again, we can't exactly compute that, so we compute an upper bound as shown. And then we can combine all the errors. So we have the Holder bound error as well as the numerical evaluation error to be able to compute that G evaluated at the root is somewhere contained from this number and the given error. So let's say our error that we computed was too big. Well, what we then need to do is compute a better root approximation to shrink this error. And then we also need to worry about precision in order to handle the numerical error obtained just from evaluating. So we approximate our root better, and we use more precision to reduce the numerical error in the evaluation. So for example, let's illustrate this for polynomials. Suppose I want to evaluate a polynomial with a posteriori known epsilon bound at a root. So what is our algorithm to do this? Well, we first compute a root approximation with this error epsilon, just to have some context of where we're looking at. And then we compute a local Lipschitz bound on the ball centered at x star of radius twice that. The way we do this is because we're going to need another approximation, and we take 2 epsilons so that we don't leave that bigger ball. And so the local Lipschitz constant is just anything which is bigger than the maximum of the derivative on the ball. And so we can use the derivatives, this sort of Taylor series expansion centered at x star, to be able to bound the derivative. Since g is a rational polynomial and x star is a rational point, we then have a rational Lipschitz constant. From there, we can then compute a new root approximation where the error is epsilon divided by the maximum of 1 and this local Lipschitz constant. And then as soon as we have that new x star, we evaluate our function there, and we're guaranteed to have the error at most epsilon. So we use the initial epsilon to give us a local range. Every polynomial is local Lipschitz continuous. And so we need to compute that Lipschitz constant. And then from there, we can decide how close we need to be to the root so that we can evaluate with a bounded error. So we developed Maple code from this algorithm to be able to compute certified approximations. So let's say we want to compute a certified approximation within 10 to the minus fifth of the minimum of this function here. So the minimum exists because it has even degree, so it's bounded below. So we want to compute g at each one of the roots of g prime. So there are 2 roots. X equal to 0 has multiplicity 2. So when we do our computation, the first thing we do is take a square-free factorization so that we reduce everything to the multiplicity 1 case, but we do record that multiplicity. And then we can evaluate, and we get 3. And then we have the other root, which we approximate by this rational value. And when we compute the function evaluated there, we have a certified approximation of the minimum to within 10 to the minus fifth is somewhere around minus 91.66, etc. We can extend from polynomials to rational functions, which are defined at the roots. So what that means is the denominator is non-zero. So we can bound the derivative by using the local Lipschitz constants of the numerator and the denominator. So let's see how we do that. So for all of the numerators, we want to bound above. So because these are Lipschitz continuous and thus Holder continuous, we can bound on any fixed domain. So here's our compact domain, the ball at x star of radius epsilon. So then we know that a of x, the absolute value of a of x, is bounded by a of x star plus the local Lipschitz constant times the radius epsilon. So we can bound the numerators from above. And then the denominators we want to bound below and have it be non-zero, not zero. And so we need epsilon small enough so that when we evaluate a at x star, a is whatever the denominator polynomial is, we need that to be bigger than L times epsilon. So we shrink epsilon in order to have this condition. And then once we have that, we know that A is non-zero on that ball, and in particular, the value of A of x is greater than or equal to A of x star minus L times epsilon. So we use this local Lipschitz and therefore Holder continuous bound to be able to compute this lower bound that bounds it away from zero. And so then, because it's in the denominator, invert and multiply into the numerator allows us to create upper bounds on the derivative of g. So we can apply this method to zero-dimensional polynomial systems. So one way is to compute what's called a rational univariate representation. So what that does is that computes a univariate polynomial q and then evaluates rational functions that give you the coordinates. So for example, here are two polynomials and two variables. Has degree 6, so there are 6 equations here. And when you compute a RUR in Maple, this is its outcome. So Q is a degree 6 polynomial. And then what you need to do is you need to evaluate x and y, these rational functions, at the roots of Q. And that gives you the roots of x. So we can apply our method to be able to bound evaluations of these functions x and y at the roots of q. And so the Maple code that we use to develop this, we applied the epsilon of 10 to the minus fifth to these functions. And here are the certified evaluations of them, which means that these points listed are guaranteed to be within 10 to the minus fifth of actual roots of f. And this, all this uses is this Lipschitz continuous property applied to the rational functions in this RUR. So in summary, what we have developed is algorithm and software for certified evaluation of Holder continuous functions at a root of a polynomial. So why should we care about Holder continuous functions? Well, the reason is that these form a broad class of functions, which because of their Holder condition, we can get certified evaluations from them. Of course, every analytic function is locally Lipschitz, which means their exponent is 1. And it also includes lots of other functions which show up in applications, absolute value, nth roots, as well as the Weierstrass function in fractals and Brownian motion. For the polynomials and rational functions case, our software has a method built in to be able to bound the local Lipschitz constant near each of those roots. And so we don't need to provide that information a priori. It's computed from the approximations of the roots. And our future work is to apply our method to be able to certify non-negativity of a certain function evaluated at roots, as well as extending this to the multivariate. So I want to thank you for listening to my talk, and I hope to be able to answer questions at a later time.